Hi guys. Quick explanation before we get started. I actually created this video last year when I was teaching alongside Pete. And so a couple of times I make reference to things that Pete would have said last week. Those should be things that I said last week. So if you hear me refer to something Pete may have said and you're trying to remember what he said a year ago, I'm actually talking about stuff that this time around I taught you last week, as opposed to when I actually made this video. It would have been Pete who taught the material the week before. So let's get started. Here's what we're going to cover on today's slides. First, we're going to look at the sine waves. So when I say there are three different varieties of AC, three different versions, they are three separate sine waves. So the sine wave represents AC. It increases, it maxes, it returns to zero. It increases in the opposite polarity, maxes, and returns to zero in a sine wave. If I draw one of these very quickly for you. So just increase, peak, back to zero, decrease to a negative peak, back to zero. There's our sine wave. Okay, we use sine waves to represent AC power because that's exactly what it's doing. However, it can get very complicated and very messy very quickly. And so that introduces us to the idea of vectors. And if we can use a straight line, which is what a vector is, if we can use a straight line to represent that sine wave that I just drew, it really cleans things up and it makes it a lot easier conceptually for the purpose of learning, but then for the purpose of doing the math. So we're going to learn a little bit about vectors, and then we're going to have some conversation about phase angles. And Pete talked about this, well, the same idea last week when he talked about cutting angles. So the cutting angle creates what we're now going to call a phase angle, which will make sense when we turn that sine wave into a vector. Okay, so we're going to do a bit of that. That's going to lay some of the foundation for future work. We're then going to get into the connections, understand how we hook something up in a three-phase system, how we hook up a three-phase load in that three-phase power system. And finally, we're going to spend lots of time doing calculations. There's all kinds of math to do based on how we make those connections. So that's what we're going to cover here in this video. So this is an image that you saw last week in the very end of Pete's presentation. So this is our three-phase alternator. Okay, so what we have here are three separate sets of armature windings. So we see a red coil, a purple coil, and a green coil. Okay, and we have three separate sets of slip rings connected to each of those three coils, and they're rotating through a steady magnetic field. Okay, so this is where the sine wave output comes from. We saw this, Pete showed you this last week. Based on the cutting angle, okay, we get a gradual increase and decrease and changing of direction as any one of those wires travels through 360 degrees of rotation through that magnetic field. Okay, so by placing three of them in there, that's how we get our three-phase. Now, it says that those windings are separated by 120 degrees, which makes sense because then you've got three of them, 120 degrees from the first to the second, 120 degrees from the second to the third, and then 120 degrees gives you a full 360 to bring you back to where you began. So that gives us a perfect separation of our three phases. Here's what it looks like if we take a closer look. Okay, we've actually changed it. This picture shows us the exact opposite. Now our windings are stationary and it's the magnetic field that's cutting through them, but the result is the very same. Okay, so we have phase 1 is green and it's at the 12 o'clock and 6 o'clock positions, and then it's actually 60 degrees later that you find phase 3. Okay, so I'm looking here, here's phase 1, okay, and then 60 degrees later, this, and it's called phase 3 because what you have to do to find the 120 degree separation from the first green coil that I circled, 120 degrees later, we find the first of the two blue coils. Notice that the blue coils are referred to as phase 2. Okay, so there's our 120 degrees of separation, but when you have pairs of poles, you find a pole every 60 degrees. Okay, but it's then another 120 degrees from this pole, the blue winding, 120 degrees later gets you to the yellow coil, which is phase 3. Okay, so is that completely confusing, or can you see that? We've got, and then here's the final 120 degrees from this coil, brings us back to this coil at 12 o'clock where we started. Okay, so that's the 120 degree separation, but you actually find a coil every 60 degrees because the coils are placed in pairs. Okay. Now, before I move on to the transformer conversation, let's talk for just a moment about the advantage of three-phase over single-phase. Why three-phase? Okay, what happens is, let me draw my ugly sine wave again. So there's the first sine wave, and if I can get really creative, I can change colors for you, and I can draw a second sine wave 120 degrees later. That's probably not even close to 120 degrees. And let's try green, which I think goes about there. Okay, now, if we ignore the blue and the green for a second, and we go back to that first red sine wave that I drew, in single phase power, when you have that single phase power running down a line, you have periods where there's 0 volts. Okay, and so the voltage is pulsating with many, many periods of there being what we call null voltage. So there's nothing, okay? We eliminate those periods of null voltage when we move to a three-phase system, okay? When there's nothing on the red phase, there's something on the blue phase, or there's something on the green phase, and there's always voltage traveling down the line, okay? So you don't get the same pulsation effect. It's a much cleaner power. It's a much more consistent power, and that's one of the primary advantages of the three-phase. Okay, so let's move into the transformer conversation now. So we've already looked at the transformer construction, and we understand that from a single-phase perspective. Here's what we see with a three-phase transformer. So it looks like an H-type core. Okay, but what we have are both the primary and the secondary windings of each of the three phases wound around one post of that core. Okay, now so this is a three-phase transformer. Okay, you can also build a three-phase transformer bank using 3 single-phase transformers. Okay, we can do the same thing, we can do the same math. In terms of the rest of our conversation here in today's slides, when we get to the calculations at the end, it doesn't make any difference. Okay, 3 single-phase transformers or 1 three-phase transformer, all of our conversations are identical. Okay, so here's a sine wave. These pictures are going to be much prettier than what I attempted. Okay, each of the 3 phases of an AC waveform with exactly the same period and frequency. Okay, so they're identical in every way. Okay, their frequency, their period, their magnitude, everything about these 3 voltages is identical except for that phase shift. Okay, so that's the terminology. Okay, there is a shift in the phase, shifting of when that sine wave crosses 0 or peaks positively or negatively, okay? And they're out of phase by 120 degrees. So there's a couple of different ways that we can talk about that. There's a mechanical separation and there's an electrical separation, okay? So these 3 coils, oh, I'm still on the green, cool. These 3 coils are mechanically separated by 120 degrees. Okay. As a result, A, B, and C sine waves are electrically out of phase by 120 degrees. Okay. We could go back to the design of our alternator, and we could double up on everything. Okay. So instead of 1 A phase and 1 B phase and 1 C phase, we could have 2 of each. Okay. And what we would do is we would we would shift, I can't see my pointer, there it is. We could shift this sine wave. So this is 360 degrees, okay, in terms of the sine wave from start to finish. And it's 360 degrees of rotation that gets us there. But if we were to double up on the coils in the alternator, the result would be that electrically, we would see this 360 degrees, a full sine wave, but we would get there with only 180 degrees of rotation within the alternator, okay? So instead of traveling 120 degrees physically, we would in fact only travel 60 degrees physically, and we would still see 120 degrees of electrical shift, okay? Not to be confused with the slide a little bit earlier, we did see a phase every 60 degrees, but that was because they were paired for a single phase. I'm talking about two completely separate phases, which would double the frequency of the sine wave. We would get 360 degrees electrically with only 180 degrees mechanically. Okay. Not something we typically see, but something to understand that there's a difference between the mechanical degrees and the electrical degrees, potentially. But for our purposes, they're both going to be exactly the same. So here's the thing, is when we're looking at those sine waves, things can get complicated really quickly. And so let's move away from that and replace that sine wave with a straight line, with a vector. Okay, so vectors are lines that indicate both magnitude and direction. All right, so that first vector we see on the horizontal says it represents 7 volts and it is at 0 degrees. Okay, so we have a magnitude, 7 volts, we have a direction, 0 degrees. If we take that vector and we point it straight up, as in the second example, okay, now this one actually tells us that this one is 5 amps, that's what that vector is representing. So the vectors could represent voltage, could represent current, but now the direction is at 90 degrees. And when we're identifying a direction, we always start at the horizontal on the right. Okay, so that's the first vector at 0 degrees. That is our starting point. Okay, and as we move forward, okay, so remember, let's draw the sine wave here for a second. So here's our sine wave again. Okay, remember we're moving forward in time. All right, so this is the beginning. All right, as the armature rotates through 90 degrees, okay, we are now electrically at 90 degrees. And remember that represents time. So when we're plotting a sine wave, the horizontal axis is time. Okay, but we don't express it as time, do we? We don't really ask the question, how fast is the armature rotating? How much time does it take? Okay, when we're talking about periods and frequencies, we do. Okay, and I can tell you that in North America, that sine wave happens 60 times every second. So we have a frequency of 60 hertz, which means there are 60 sine waves every second, which means that one period takes 0.17 seconds. 0.17 seconds. Okay, we could do the math. We're not going to. Let's move on. But the point is that this is time. This is the passage of time. But we don't express it that way. We express it as a passage of degrees as we move through that 360 degrees of rotation and the 360 degrees electrically of the sine wave. Okay, so when we talk about the direction of a vector, we talk about the passage of time as degrees as well. And so this reference point of 0 degrees is where we begin. And then as we move forward through time, looking at our sine wave, our vector is going to rotate in a counterclockwise direction. Okay, and so this vector is at 90 degrees. It's 90 degrees beyond the 0 degrees reference point, which is the horizontal to the right. Okay, so that's how we express vectors with magnitude and direction. So let's come back to the conversation about phase angles with our sine wave. Okay, and so here's our sine wave beginning at 0 degrees and 0 volts. And then at 90 degrees right here, we have reached our peak voltage right there. Okay, now this wheel on the left, we can think about this in two different fashions. We can think about this as the armature rotating through the lines of flux. Okay, so here's the armature here at 0 degrees, and it's generating 0 volts. And the reason is we've got to spin things on its head a little bit. We've shown the pole pieces creating horizontal lines of flux, but now we have to change it up. In fact, what we're looking at here is, and I don't know whether this is north or south, but this is one of our pole pieces. And down here, this is our other pole piece. And our lines of flux are vertical, which means that this armature, as it's here at 0 degrees, is traveling parallel to the lines of flux, therefore not cutting any lines of flux. And that's why we have 0 volts generated in our generator induced in the armature at that moment in time. Okay, and this is very much like what Pete was showing you last week. We've changed it up a little bit. We've got the lines of flux now vertical instead of horizontal. We've got this armature rotating counterclockwise as opposed to the example last week that had it traveling clockwise. So we've made some adjustments, but this is the same theory, the same logic, right? So that at 30 degrees, we are cutting some lines of flux. Okay, once that armature gets up here to 60 degrees, it's cutting quite a bit more lines of flux, represented by the induced voltage that we see over here in our sine wave. And finally, at 90 degrees, traveling perpendicular to the lines of flux, we're cutting maximum lines, and that's why our sine wave peaks. Okay, so we can look at this drawing in that fashion. Okay, let me see if I can erase all this though, because let's try something different. So if I start erasing all of this, make all of this go away. I put a lot of marks on here, didn't I? Okay, we can even eliminate our pole pieces. We don't need them anymore. Because what we're going to do now, okay, so that was kind of step one to get from the armature to the sine wave. What we're going to do now is we're going to take that sine wave and we're going to simplify it with vectors. Okay, so what I could do is, I'm going to go back to my red, is I could say that maybe is a vector. Okay, the problem is in the previous slide we said that was 7 volts at 0 degrees. We gotta carry on with this conversation. There's a little bit of a problem there, but then there's another vector, and then there's another vector, and finally here's the one that really matters. Right? Whoops. Ooh, let's try to get that straight up. Oh, that's much better. There's a vector right there pointing straight up at 90 degrees. Okay, that represents our peak voltage. Okay, so we could draw this as a whole bunch of vectors spinning around a point, okay, to take the place of the representation of the sine wave. All right, so we can bring that sine wave back to vectors to simplify the conversation and the picture. Okay, that's what we're doing there. All right, let's move on. What do we talk about next? So more conversation about the vectors. The nice thing about the vectors, the advantage is now we can do some math. Okay, doing math on that sine wave is complicated because every point in the sine wave is a different value. Okay, so if we can take the sine wave as a whole and replace it with a vector, we can start doing some math. So if we take voltage A and we replace that sine wave with a vector, okay, we're going to place it right there. And we're going to give it a direction of 0 degrees just because that is logical. It makes sense. Let's start at the beginning. But as I showed you in the previous slide, how that vector rotates through the full 360 degrees, we could in fact put that vector in any direction. Okay, it doesn't matter. It doesn't change the math, because what we're going to do now is we're going to look at the second vector. Okay, so the vector representing the voltage B. And so here it is, the 20 volt vector, and we're going to place it also on 0 degrees. So this is the point, is that whatever direction we chose to have vector A pointing, vector B must point the same way, because both of them cross through 0 at the same point, peak positively at the same point, cross through 0 again at the same point, peak negatively at the same point, and finish their 360 degrees of rotation at the same point. So the statement that we make is that these two sine waves are in phase. Okay, there's no phase shifting taking place. They are in phase, which means the two vectors that we draw representing these two sine waves are in phase, which means they're pointing in the same direction. Whatever direction we chose to point them at, we chose 0 degrees. We could have put them at 106 degrees. The point is they would both have to be in the same direction. And so now we just add them up. So the question is, when we take these two voltages and we put them in a circuit together, what's going to be the total voltage of the circuit? And the answer is our 30 volts plus our 20 volts gives us a resultant voltage of 50 volts. Okay, we just add them up. Okay. Now, here's what our three-phase waveforms look like. Okay, so this is what I was attempting to draw earlier. Didn't do a very good job. This is much better. We have phase 1, and it peaks, and then phase 2 peaks 120 degrees later, and phase 3 peaks 120 degrees after that. Okay, same frequencies, same magnitude of voltages, okay, but each one of those sine waves are out of phase by 120 degrees. So that was pretty messy. We could replace it with this. Okay, here are our three vectors. This represents the very same image as the previous slide. We have sine wave A represented by vector A, which we choose to place at 0 degrees, because let's start at the beginning. Okay, and then sine wave B is represented by vector B, and this vector is the same magnitude, which means the line is the same length, but it comes 120 degrees. Well, this is actually showing it 120 degrees before, isn't it? Okay, but in fact 120 degrees after. All right, kind of doesn't matter. We need 120 degrees separation, and we're in business, because another 120 degrees of separation brings us to sine wave C, and finally 120 degrees brings us back where we began. Okay, so they're just endlessly chasing each other around the 360 degrees of rotation. All right, always separated by 120 degrees each. All right, so this is an awful lot tidier than that image of the three sine waves we looked at in the previous slide. Represents the very same thing, but it's a lot cleaner, okay, a lot easier to talk about and look at and ultimately do math with. Okay, so now it's time to talk about connections. Okay, that is what three-phase is, but how do we connect it? Okay, so where should we start this conversation? It's a fairly lengthy one. We've already learned about connecting multiple loads together in a circuit. Okay, you learned this in basic when you learned Ohm's law, and you learned about series circuits and parallel circuits. Okay, when you have two electrical loads that you're going to be connecting together, are you going to connect them in series or are you going to connect them in parallel? Those are your choices. You always have to make that decision. Okay, now in three-phase, we have, this is just a single load, a single three-phase load, or we could build it using three single-phase loads, three resistors. Okay, we can take three resistors and connect them together into a three-phase connection. Okay, it's not are we connecting them in series or are we connecting them in parallel? Because it's a single load. It's a single three-phase load. But we do have to make a choice, because what we actually have here are 6 connections. Okay, so if this was a resistor, this is shown as a coil because it's a conversation about the power supply as opposed to the load, but conversation is the same either way. There's one connection. There's the other end of that coil. Let's pretend it's a resistor. There's one. Okay, and then here are the 2 ends of this one, and here are the 2 ends of this one, and we have 6 different wires that we have to put somewhere, do something with, make a connection. Okay, so this is not a conversation about connecting 2 loads in series or parallel, because once we have 2 3-phase loads, we still have to have that conversation. Okay, we could have 2 separate 3-phase loads that we've chosen to make this Y connection in, and we still have to decide, are we going to place them in series or are we going to place them in parallel? Okay, so that's a separate conversation. But if you're reading through this, you'll see where I'm going. Let's get through the first bullet first. It says that a Y-connected system has 1 wire from each phase connected together to form a common point, which we call a neutral. But this thing called Y is said to be like series, okay? And that's in quotation marks. It's like series because it's not series, okay? This is a 3-phase connection. Series, this is a 3-phase connection of a single 3-phase load. Series is a conversation about what happens when we have more than one load we want to connect together. We're going to place them in series, or we're going to place them in parallel. Okay, that's a different conversation, but we can use the rule of like series to help us get through some of the math. Now, when we get to the math, we're going to come back and talk more about what like series means, but I want you to understand that we're using a single phase concept to kind of start to understand this 3-phase connection. Okay, so it shares some of the basic traits. So that diagram shows us what a Y connection looks like in diagrammatic form, and so it makes it pretty obvious to us why we would choose to call this connection a Y connection, because it looks like the letter Y. Okay, next option. So we have 2 options. Just like in single phase, we can connect it in series or parallel. In 3-phase, we can connect it in Y, or we can connect it in... I guess I better finish the Y conversation first. Sorry guys, I got you all hyped up there, and then this slide didn't go where I expected. So this is a point that we have to be careful about how we make our connections, and this is why the vectors are so important. So if you look at the image on the top, we can see that the 3 vectors are all pointing outwards. And so that is the correct connection. Okay. The one below says incorrect, shows 2 vectors pointing outward and 1 pointing inward. All right, so that's going to create problems. That's going to create imbalances. That's going to give us a situation where the 3 sine waves are not 120 degrees out of phase. Everything doesn't line up nicely. Okay, now we could have all 3 vectors pointing inward. All right, that would be the exact opposite of the top image, and that would work just fine. The point is that we can't mix and match. Okay, no mixing and matching allowed. Now I think we get to talk about Y or delta. Good, here we are. And so delta gives us this triangle, okay? And so a triangle represents delta, and so that's the naming. So now what we've done is we've taken our 3 separate loads, which we're going to bring together into a single 3-phase connection, and we're going to close the loop. Okay, so if we were looking at vectors, okay, if we were drawing 3 vectors, and this might very well be the image on the next slide, but just like the slide with Y that said make sure you get all the vectors right, okay, if this vector was pointing this way, that would be a problem. That would be absolutely incorrect. So let me erase that. In fact, the vectors must all chase each other around the triangle. And once again, we could put those vectors exactly opposite. Okay, this shows the 3 vectors connected tip to tail in a clockwise fashion. We could place them tip to tail in a counterclockwise fashion. That would be just fine as well. Okay, So a delta connected system has the three phases connected in a closed loop. And here we go, the delta connection is said to be like parallel. So when it comes time to do the math, we are going to lean on the things that we already know about a single phase parallel circuit. Okay, we are going to be able to pull from that knowledge, apply some rules to figure out how to do the math. Okay, but it's like parallel because we can only take that so far, and then we have to abandon that and move to what we know to be true about three phase. Okay, so a Y connection is said to be like series in some of the math that we can apply, and a delta connection is said to be like parallel in some of the math that we can apply. So here we go. Here's our three vectors placed tip to tail. So a delta connection is made by connecting the number 2 terminal of one coil to the number 1 terminal of the next coil, and so on around, placing the vectors tip to tail. So we're going to go back to single phase here for just a moment to try and figure out some numbers. Okay, so here's some simple vector addition. We have a single phase 3-wire scenario. So you've got line 1 and line 2 separated by the neutral. Okay, so here we have our 120 volts is half of the transformer. So right there is 120 volts. And then we have another 120 volts, which is the second half of the secondary. Okay, and then we have what we call a center tap right in the middle of the secondary of that transformer, which is what gives us the neutral, the break between those two vectors. Okay, but they're placed tip to tail, and they're most definitely in phase, which means the total potential between line 1 and line 2 is 240 volts. It's double the 120 that you get when you look at the center tap. Okay, so all that's nice and straightforward. That makes perfect sense, right? It's all good. Here's where things get interesting. In a three-phase system, when you have a neutral, the potential difference between line 1 and line 2 is not just double the potential difference between line 1 to neutral or line 2 to neutral. And that's because of the 120 degrees out of phase. Okay, so if I were to draw this, let's draw a Y connection. I won't draw the whole thing, but let's draw some of it. So there's a coil right there. And 120 degrees out of phase, there's a coil right there. So if each of these is 120 degrees, sorry, 120 volts, 120 volts. All right, so that's from line 1 to the neutral point here in the middle, and line 2 to neutral is also 120 volts. The question now becomes, what is the potential difference from line 1? So if I put a voltmeter here, and I ask the voltmeter, what is the potential difference from line 1 to line 2? Okay, in the previous slide when we were looking at a single phase 3-wire system, the answer would be 240 volts. Just add them up. Okay, but that was possible because the vectors were in phase, the voltages were in phase, sine waves were in phase. In this scenario, they're not in phase. They're out of phase by 120 degrees. And so what is the result? Okay, anybody know what this number is? Okay, in a typical 3-phase system, we are said to have a dual voltage. And it moves on. Well, there it is. I wanted to write it down before I advance to the next slide. It's 208 volts. Okay, so the question is, if you expect 240 and you only get 208, where'd the rest of the voltage go? And the answer is we lost it because of the fact that we are out of phase. Okay, and so in fact, if you like geometry and you want to use a ruler and a protractor and really check this out, we could replace all of these units of measurement, these volts, we could replace them with millimeters or centimeters or whatever unit of measurement you choose, and it'll work out. You draw a line 120 millimeters long, you get your protractor out, you find 120 degrees, you draw another line at 120 millimeters, and then you measure from point to point, and you will measure 208 millimeters. Okay, if geometry is your thing, we can accomplish the same thing. We can see this to be true. Okay, so because the two voltages, the two phases, or we can consider these voltage rises, okay, 120 volts there, oops, I've done it again, 120 volts there. I don't know why I keep losing my pointer. There it is, 120 volts there and 120 volts there. If those are each voltage rises, then the total voltage rise is 208. Okay, so this is the secret behind three-phase and the math done with three-phase. So it looks like this. We can get complicated. What we have here is we've basically placed the Y and the delta systems both in there, got it all jumbled up. Okay, so this is the Y connection where we have a center point, and the blue around the outside is the delta connection where we've closed it all in. But ultimately, we only have a couple of numbers. We have 120 degrees, we have 120 volts, and we have 208. Now in bold here is the one thing that matters. Okay, when we're doing math in three-phase, okay, everything comes back to this number right here, √3. Okay, that is the relationship between 120 and 208. It's also the relationship between, here are some other common three-phase numbers, is 347 volts, 347/600. Right? The relationship between 347 and 600 is once again √3. Okay, so when we're doing our three-phase calculations, basically we're going to ask ourselves two questions. Okay, the first question is the value going to change or stay the same? And we're going to get into these conversations in a moment, but is it going to change or stay the same? Okay, and if we say it stays the same, that's easy, we're done, move on. If we say it changes, well, changes by how much? The answer is always √3. And then the only thing left for you to figure out is whether you have to make it bigger by √3 or smaller by √3. But a change in voltage or current when doing calculations based on three-phase connections, the change is always by a factor of √3. Okay, nice and straightforward. I mean, it really is. There can be all kinds of reasons for it to feel very complicated, but it really always comes back to that. I think actually what I'm going to do is I'm going to stop this video now before it gets any longer, start a new video, come back and actually do the math. So what we're looking at here on this slide are the variables that we're going to have to put in the right places to start doing the math and figuring out the numbers. But I think I want to shut the video down right there for now, start a fresh video, and we're going to jump into the math, and we're going to take all of this weird nebulous conversation that we've been having and apply it to some real numbers. Okay, so I will be right back. Let's shut it down there for right now.